Hello and welcome to another coding challenge. In this coding challenge, I am going to implement the system you see over here on the right called the Lorenz attractor. Visualize that in 3D, in processing, all in one session here, which will hopefully be about 10 to 20 minutes. We'll see how long it takes. I've got a timer running up there. Okay, so before I start actually writing the code for it, I want to talk about what this system is, why does it exist, why is it interesting, and how does the math behind it work on a kind of higher level, and then we'll start looking at the formulas for it and implementing those formulas in code. Okay, so the Lorenz system, there's a lot of resources for this online. I'm going to put a few in the description of this video. Paul Bork's site is a particularly useful one that I'll just mention really briefly, but I'm going to look just at the Wikipedia page here, which says the Lorenz system is a system of ordinary differential equations. Okay, so the first thing we have to tackle here is what is a differential equation? I could easily, I got a timer running here, I could easily be here for like the rest of the day talking about differential equations and confusing myself over and over again. But the basic idea of a differential equation is an equation that looks at how a certain variable changes according to other variables, how the rate of change of a variable is affected by other variables in a system. That rate of change being a differential. So let me give you an actual practical real world example that might help solidify this understanding. Let's say you have a spring. Okay, so I have a spring connected to a wall with a bob at the bottom. And you could think of this spring as having a position called y. How does its y position change over time? That's often written as the change in y over time. You could think of that in programming speak as y equals y plus the change in y, right? Every frame of animation, y changes. But it changes based on its the rate of change of y actually changes based on the y position itself. If you pull it all the way down here, how fast it's going to spring back is going to be much more than if you pull it over here. So dy over dt, the change in y, the differential of y, is a function of other variables in the system itself, y itself. This is a differential equation. And so this actually comes up all the time in programming. You have position, you have velocity, velocity being the derivative, the rate of change of position. This is something that you'll see over and over again. And here, the Lorenz system is defined by these particular differential equations. The rate of change of x over time, the rate of change of y over time, and the rate of change of z over time. Now these variables, x, y, and z, those define the state of the system. But I'm going to use those literally as x, y, z positions to visualize to get this particular structure. So if I look at those values, the state x, y, z over time, and draw them with colors and lines, I'm going to see this particular system. So why is this system interesting? It turns out that the Lorenz system, which was invented or discovered in 1963 by Edward Lorenz. He was studying meteorological conditions, the flow of the atmosphere, this type of thing. It's one of these chaotic nonlinear systems, meaning whatever the inputs you feed into the system, you feed some inputs into the system, you calculate that system over time. It's a deterministic system that will produce an exact result every time with the same inputs. But if you change the input ever so slightly, you could get a wildly different output. It's nonlinear. A tiny change to the input makes a large change to the output. This is the butterfly effect. A little butterfly flaps its wings, changing the air just a tiny bit in the outside on one side of the world, and on the other side of the world, a giant volcano erupts. Okay, so this is this idea of a nonlinear system. It's chaotic, it's unpredictable, and a lot of these types of systems exist in nature, and this is one particular example of a model of that type of system. Okay, so now let's look at these formula, and let's try to figure out how we're going to actually make this happen in code. I think we're ready. So we know that I need three variables, an x, a y, and a z. So let me go to my program here, and I'm going to close this one, and I'm going to start writing some code from scratch. And I am going to give myself an x and a y and a z. And I'm going to give them some initial values like that. Okay, so we're good. So I solved those equations. I know I need an x, a y, and a z. So that's a good start. Now, one thing I should mention really briefly as I'm about 5 minutes into this is that notice I defined those values as floats. if you look at examples you'll find on the internet, often the data type that will be used is a double. A double being just like a floating point number, but having more decimal places. And sometimes with these systems, you really need a high degree of accuracy. But I'm just some person here on the internet programming colors and things on the screen. I don't care if it's a little bit not so accurate. And float is a bit more native to processing, so I'm going to use floats. OK, so now what I need to figure out is I want to kind of implement these equations. So let's just start with x. The change in x over time equals sigma, that's the Greek letter sigma, times y minus x. So first of all, I can't use the Greek letter sigma easily in my code. So sigma, I'm going to make A, rho, I'm going to make B, and beta, I'm going to make C, which I realize is a bit confusing, but that's what I'm going to do. So those are constants, by the way. I need constants for those values. So let me go back to my code, and I'm going to say a float A equals 1. So I'm just going to start with the constant 1. Now, what I'm going to do is have this particular calculation happen over and over time, right? It's supposed to happen over time. This is the interesting thing about this. Those formulas, the change in x over time, those formulas are talking about real life time that's continuous. Our time in processing is frame by frame by frame. So every cycle through draw is 1 unit of time. So what I'm going to say is that the change in x equals that constant times what? Y minus x. Y minus x. And now x equals x plus that change in x. It's really that simple, right? I'm just taking that exact formula that says the change in x over time equals the constant times y minus x. And now change in x just means change x by that value. X equals x plus dx. So I can actually start to go and implement y and z, the change in y, and the change in z. And now I just need to go back and refer to those formulas again. X times b minus z minus y. Oh god, I hope I get this right. This is hard to do. Oh no, sorry. X times b minus z times y. Did I get this right? Minus y. I want to have spaces there. What's wrong here? Oh, it doesn't know what b is. I'll fix that later. And now the change in z is x times y minus c times z. So it's x times y minus c times z. So this should be good. And now I just need to get some spacing here. And I need to also add 2 more constants. Float b equals 1, float c equals 1. And now I need to just change x, y, and z. X, Y, Z. X, Y, Z. Y, Z, dy, dz. Okay? So this is the idea. I implement those formulas directly from the Wikipedia page to calculate the change in x, the change in y, the change in z, and then actually change them. Now here's the thing. What is my time? There's a weird sort of thing that I'm going to bring up here, which is my time step. So right now, every frame is like a singular unit of time. But the pattern that I'm going to draw, right, is going to look, I'm not going to be able to draw, it's going to look something like this. And in the sort of continuous world, I was moving this marker continuously. But in the processing animation world, I have point, 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 point. So how close, and I might connect those with a line. So do I want to see my result look like this? Or do I want to see it as a more continuous curve? How fine do I want those to be? And that's the sort of dt, right? If you think about, oops, I'm going to come back over here, right? Really, I'm saying dx over dt equals something. So what I want to do is actually take that something and multiply it by dt. What is the change of time for each frame? So what I'm going to do is also introduce a variable called dt. And I'm going to say it's like 0. I'm just going to make that 1 for right now. But I'm going to take the whole thing and multiply that by dt for each one of these to sort of scale. And I'll show you how different that's going to look as I continue doing this. So now we've got those formulas implemented. Now we've got to see, is anything working correctly here? So I need a way of figuring that out. The first way I'm going to do to figure that out is first just make sure the program runs. I'm going to add a black background, and I'm going to run it. And OK, so I don't have any errors. That's a good sign. One thing I could do is I could say print line x, y, z. So I could sort of look at what's being printed out. Now notice something here. all I'm doing is getting the values of 0. So there's a little bit of an issue here, which is that doesn't make any sense. So I can't start with 0, 0. If I start with 0, 0, 0, these formulas are only ever going to produce 0, 0, 0. So I got to modify the inputs a little bit. And I'll just start with x as like 0.01. That should do pretty well. And if I run this again, we should see, like, look, I'm getting some interesting values there. Now, what are these values producing anything of note? Not really, but why not? Well, because my constants, I just made my constants 1, 1, and 1. So the Lorentz attractor works a particular way based on what those input constants are. So if I go back to the Wikipedia page, I could sort of find somewhere on here, it's going to give me some values I could use. Like sigma equals 10, rho equals 28, and beta equals 8 divided by 3. So let's use those constants. I believe sigma was A, B was 28, and C was 8 divided by 3. And I'm going to do that just to make sure I get a floating point value. Okay, so I think that should work. I'm like skeptical, and we should see, ooh, not a number. Okay, so what have I done wrong here? I might have to time out this video, see how long this debugging takes. And this might get edited out if it starts to take a really long time, but let's look here. So what have I done wrong here? X, Y, Z. So let's comment out and just do X for a second and see what I get. Oops, and I just want to look at X. Oh, I had some numbers, and then I got not a number for Y. So I might just be like, 1 is a terrible number for dt, because I'm like, it's as if I'm teleporting myself through time massively fast. So let me just make this 0.01. Yeah, okay, this is more like what I expected to see, although those numbers are getting incredibly small. I hope I implemented this right. I have to check my formulas. But let's go back here and see if I'm getting some reasonable formulas. Okay, good. Okay, so this is better. This is what I expected to see. Okay, great. So now I'm seeing some numbers that make more sense. So my issue there was literally just having, and maybe that won't get edited out, was just having the number 1, and it just sort of went off to infinity super fast. These systems, they don't have a recognizable repeating pattern, and they'll often tend towards infinity or some like non-existent value. Okay, so let me go back to 0.01. Now I want to be able to figure out, is something actually working here? So the first thing I'm going to do is just say stroke 255, and I'm also going to translate to the center of the window. And I'm just going to draw a point, and I'm just going to do this in 2D. So I'm not going to worry about the z. I just want to at least see, like, let me plot the state of the system over time with x, y. So let's do that. And, good, this is very good. So it looks like I did the formulas correctly. And you can start to see, like, that's something there. So we're kind of like, we're trucking along here. I've got the Lorentz system, like, sort of visualizing right now. So really, basically, I'm done. However, I want to make this look like something. I want to make this look like a 3D shape. I want to maybe add some color to it. I want to be able to spin around it. I need to do more with it. Maybe I want to be able to like explode it so that all the points should like fly off of it and come back. So I want to do, even though in 13 minutes we kind of got the math down, I want to do more with this in terms of the visual output of it. So let's go forward with that. So the first thing that I'll do is let's just go ahead and work in 3D. So I'm going to change the renderer to P3D, and then I'm going to add the z point. So we should see now that it's the same. It looks pretty similar, but there's actually a z value there. Now, one thing I want to add also is just I want to use the processing function scale. So scale is a transformation you can add to your scene to kind of like stretch it out a little bit. We might be able to get this through zooming in and out as well, but I just want all the points to be sort of spaced out a bit more and look a little bigger. So I'm going to basically scale everything by 5. So we can see, yeah, so now I kind of have a bit of a closer view. You can see all the points of the Lorentz attractor are being plotted in 3D. Now here's the thing. How am I getting all these points on the screen? I'm just drawing one point at a time. Well, notice how my background is in setup. So this worked just to see that the system was working, but it's not going to be a very good solution for eventually over time being able to manipulate this system. So what I need is some sort of data structure, some sort of list that I can store all the points of the Lorentz attractor. So let me do that. And what I'm going to do for that is an array list. And this is where we might rather be in JavaScript, and I'll try to make a JavaScript version of this as well. I'm going to call that points. I'm going to make that a new empty array list. So this is the syntax for something in Java called an array list, which is a flexibly sized array, something I could just add to, and I'm calling it points, and the data that I'm going to put into that array list are p vector objects. Why do I want a p vector object? It's because every single frame, I'm going to say points.add a new p vector with that x, y, and z. Okay? So I want to add a new vector with x, y, and z to that particular array list, and we can see that this is still working. Nothing is broken yet. And what do I want to do now? As those points are being added over time, I want to draw all of them because I need to erase the background, right? So let me just show you what I mean. I'm going to move this background to draw. This is actually going to produce kind of an interesting result because now you're going to see this point. I kind of love this. Just moving along the pattern of the Lorenz attractor. It's kind of this beautiful, interesting, kind of chaotic motion. I just want to stop and watch it. But I'm 15 minutes in. I want to see if we can wrap this up in about 20 minutes. So I'm going to keep going. So what I want to do is instead of just drawing the existing point, what I want to do is say for every vector v in that array list points, draw a point at v.x, v.y, and v.z. So I'm now saying instead of just drawing the current point, loop through, and this is known as an enhanced loop in Java, for every vector v in the array list points, draw a point at vx, vy, vy, vy. Back after a technical hiccup, you can see that the entire Lorenz attractor is drawn with each element as a separate point based on every p vector that's in that array. So really, essentially, I'm done. There you go. It's in 3D. That's the entire Lorenz attractor shape. But I do want to add some more things to this and give you some exercises to think about what you might do with this. So first, let's just change the way we're drawing this a little bit. One thing that I could do is connect all of the points with a line. So instead of drawing everything as a single point, I could actually set the vertex of a shape. So if I say begin shape before I draw all the points, and end shape after I draw all the points with vertex instead of point, what that's going to do is connect every point. And you're going to see now that, whoa, it's doing it, but it's actually trying to fill it in as if it's an entire shape. So there might be some interesting things I could do with that, but for now I'm just going to add no fill. And we're going to be able to see now this continuous line. So I could zoom into it and sort of see that every point is now connected, right? So now we have this continuous shape, which is a nice start of sort of seeing how I could sort of tinker with how this is visually. I could also try to come up with like a clever way of changing the colors of it. I'm sure that you, as a wonderful person on the internet with visual design talent, will do something much more interesting. But I'll just show you really quickly. I already have that in there because that was from the technical glitch. But I could add something called color mode. And I could change the color mode to HSB, meaning hue, saturation, brightness. So what I could do is set the stroke with some sort of hue, a saturation of 255, the maximum, and a brightness of 255. So I'm now as I draw it, it's going to have a particular kind of like turquoisey, greeny hue. And why not, while I'm doing this, make a variable, start it as 0, have that variable be the hue, and for every single vertex, increase that by some value, and then if it goes above 255, reset it back to 0. And now I should get, why not have a rainbow, since this is coding rainbow, a rainbow Lorenz attractor pattern. So you can see as the color is changing, we've got kind of yellow, red to yellow to orange, and that sort of thing. So really, okay, so the last thing I want to mention. So what's interesting about what I'm doing with this particular strategy, separate from the Lorenz attractor algorithm itself, is the fact that every one of these points is saved in memory in that array. So one thing I might just demonstrate to you is the fact that those points can be manipulable in real time. So for example, one thing I could do in processing is I could write a vector called offset. And I could say pvector.random3d. That's going to give me just a random unit vector of unit 1, of length 1 pointed in a random direction. And I could add that offset to every single vector in the Lorenz attractor. Now if I run this, it's kind of going to go crazy because the unit of I've scaled up by 5. So you can see it's like shaking and jiggling like crazy. So what I could do is maybe shrink that offset down quite a bit by, make it 10% of the length of itself. And you can see now, if I zoom into it, you can see how the points are kind of moving ever so slightly in space. Now, I'm not suggesting that what I've done is a particularly magnificent result, But what if you had all those points move along a sine wave? Or what if you had those points expand out and then come back to their original location, or morph into another shape, or fill in the blank of your interesting idea there? So what I think I would like you to do, now that you've seen how to program this Lorenz attractor from scratch, first, you don't have to do anything. You're just watching this video. Maybe you want to go outside and toss a Frisbee around or eat some lunch, which is what I kind of want to do right now because I'm feeling a little woozy. But I think what would be interesting, what I'd be excited for some of you watching this video to explore is what types of how can you put your own design spin on this particular shape? What happens if you start to manipulate the variables, right? Here are the constants that I'm using. Make up your own constants. Look up on the internet some other known constants for the Lorenz attractor that produce other kinds of shapes. What happens if you change the dt variable? What can you mess around with these formulas and get something else? Could you go to a site and find a different kind of attractor that's not the Lorenz one? There's a lot of these under the sort of category of strange attractors. So try to make your own version of this. Be creative, play, experiment, don't worry too much, and share with me your results. But this has been, hopefully, something you've enjoyed, which is programming the Lorenz attractor from scratch in processing in 3D. Thank you very much for watching. I'm thrilled to have finished this because you might not know there was about a 45-minute audio problem. I really hope the audio is working right now, and this is actually the end of this video. Thanks for watching, and I'll see you in the future in another video. Goodbye.